So a few words about myself. As Paul introduced me, I'm a network engineer at Facebook. So this weekend, Paul pings me. He tells me, hey, stop working, do some slides instead. And it got to be something about IPv6. And so luckily, we have this technology called ILA, which we use to implement virtual networking. And so this talk is about this. So let's get going. So first of all, this is a pretty much question which is rhetorical. What is virtual networking? If anyone knows the answer, let me know, because I got lost a while ago. People have lots of different definitions for this content, for this term. I mean, like, we have tons of things, right? We have VXLAN, we have GRE, right? So who likes VXLAN, by the way, in this audience? Anyone? Yeah, not so many fans. Anyone likes GRE better than VXLAN? Even worse, right? So the problem was people still struggle to define, hey, what does this mean? How to use it? There's lots of proposals, lots of technologies. And so when we try to approach this internally, well, we spend lots of time arguing about this, definitely. And then we sat down and tried to define a problem. So the problem was straightforward, to be honest. So as you all know, containers are pretty hot or cool today. I don't know. So Facebook definitely has its own version of containers. It's actually been around for a while, even before Docker was out. It's called Tupperware. So Tupperware is the thing that does manage our infrastructure in an elastic way. And so Tupperware, you can think about this as a combination of Docker and Kubernetes. So it's a system for packaging the processes, the images, deploying them on machines, doing resource allocation, all this kind of stuff. So I guess people at least heard about Docker. So they kind of built some connection. So when we built this initially, we lived a very naive way. We deployed containers on all machines. Every machine had one address. And when you had to kind of fight for the ports on this machine, you have like 10 containers, you have to allocate 10 ports. And it was pretty painful. I mean, it wasn't like difficult, but it kind of led to very clumsy code in the scheduler and other parts. So ideally, our first requirement was, hey, can we have one IP address per process or container, whatever? Which seemed impossible with IPv4, because IPv4 was already exhausted, and by that time, we had v6 everywhere. And so we say, OK, it would be super nice if we can have a v6 address per container. And second was kind of fancy. I said, hey, it would be super nice if you can make this address mobile as well. So once you start the container, you give this guy an IP address. And as you move this container around, you keep address the same. So effectively what you do is IP mobility. Or like in a more fancy words, you separate names from locators, which has been a very hot topic. I mean, maybe 20 years ago, maybe 10 years ago. I mean, it keeps coming back and forth, right? People discuss this. Seems to be kind of cool. So our difference, like if you look at all these virtual networking proposals, people usually have separation, right? So you have different virtual networks which are live in isolation. Like if you take VPNs, L3 VPNs, BGP VPNs, they can have the same address space inside them. So in our case, there was no isolation. So what we have, containers, they run in a flat address space. Everyone draws addresses from the same pool, and there is no any kind of separation. And second one, so basically around the time when we started working on this, I think Tom Herbert came up with his proposal called ILA. And in this section of the talk, we're going to talk about ILA in details, discuss it, the implementation, theory behind it, and then go over deployment. So first of all, does anyone remember ILNP? Anyone at all? So ILNP, yes, used to be hot. How many years ago? 12, maybe 13. When there was a lot of arguments about scaling the internet, right? It was a big area of discussions. It was this great curve, hey, BGP will explode, we'll all die, and the internet will collapse. And so back then, there was lots of proposals to scale the internet addressing, and one of them was ILNP. So ILNP was specifically around IPv6. So back then, 2006, right, was almost no v6 anywhere, right? But people already liked it a lot. So the idea was, OK, we have this big, gigantic address, lots of bits. So let's take this address and split in two halves. The locator, which was upper bits, the ones used for routing. So when you send a packet, you use these bits to send packet on the internet, and identifier. So identifier was supposed to be immutable. So you have a split, and this split idea is not nothing new, right? I think people came up with this idea maybe 1998 or something. It was called GSC. But you know, the same ideas keep popping up back and back, so over and over again. And so the next thing was, OK, ILNP idea was, once we have a machine, let's give this special address, which has two portions, locator and identifier. As machine moves around, say its mobile device, we keep the lower portion, the 64 bits, immutable, the same. And then we change the locators. So as machine moves around, we change the attaching points, and we change the locators. And ILNP proposed back then to store all this association between the ID and locator in DNS. So back then, this was like, hey, it's cool, DNS is scalable, and so on and so forth. And as I mentioned, there was two goals behind ILNP. Provide multi-homing. Because I think the still unsolved problem is like, how can we provide multi-homing in a scalable way, such that we don't have to leak prefixes everywhere? And of course, scalable internet addressing. As I mentioned, back then, people were afraid that we'll pretty much run out of capacity in the FIBs in the routers. So ILNP had one major issue. The transport layer, TCP, had to be aware of the locator changes. Because you keep changing the upper portion of the address, you have to modify TCP stack to, say, change checksum computation, right? And then you have additional messages in ICMP and all other stuff. So in the end, the idea was you have to change TCP IP stack. And this was the major impediment for deployment of ILNP in the internet. I think like it never went beyond the pure theory. It was a bunch of great RFCs. It's a very good read if you're curious. There was maybe some code produced, which I never seen working. But it remains still an open topic in research in academia. And once again, the reality is nobody wanted to change the TCP stack on all the hosts in the internet. So ILA tries to address this major problem. It tries to say, OK, we'll take ILNP idea of this split, of this locator and identifier split, but we'll avoid modifying the TCP stack. So first of all, the idea was, OK, we won't tell TCP that the upper bits, the locator, are changing. Next one, to make this happen, we'll simply replace the locator with a SERP prefix. SERP prefix is a fixed 64-bit string that never changes. We'll discuss this in more details later on. But back then, Tom came with this idea. Tom Herbert, he did some implementation in Linux kernel. And they say, hey, it kind of works. You know, you don't have to change the TCP stack, but you have to implement net translation in kernel. So definitely have to do some magic, right? You have to do something in the kernel, but you don't have to modify the other machines. And so even though it's NAT, and everyone knows NAT is evil, it was stateless NAT, so it's kind of very simple to implement. So just like ILNP, just remember, because ILA comes from ILNP, ILA imposes some requirements on the host. So ILA host has to maintain a few additional things. So first and foremost, the biggest change that you have to implement is to allocate every host a /64 prefix, the locator. So this is very different, right? We're all used to, OK, we have a /64 subnet, we get these host routes from it, we have NDP, SLAC, DHCP, whatever. But now you have to have an additional full /64 prefix in every host, which means like a lot of new allocations. Of course, every host in the kernel has to maintain this mapping cache. So you have to maintain association between the identifiers and locators. And so this cache is very similar to kind of ARP or NDP cache, but it's purely for IP address rewrites. It's a NAT table. And pretty much the kernel has to maintain this cache and apply it to packet rewrites. And the last, but probably not the least, is this very important thing. ILA has a concept of ILA Router. So this is something which was missing. It was never present in ILNP. This is the gateway that allows the non-ILA hosts to talk to ILA, like ILA domain. So this was the gateway for transparency, right? It allows you to allows things to coexist. You may have ILA machines which have all these caches, all these logical addresses, identifiers, and non-ILA machines can still reach them via these gateways transparently. So you don't have to change everything at once. This is basically the biggest, probably, practical requirement. You don't have to change every machine at once. You can do this gradually. OK, so now some diagrams, finally. Let's see how things work in the ILA world between two ILA hosts. So first assume we have this logical prefix, Facebook, right, /64. This is the fixed prefix that you always see in the transport layer. We have host 1, which has a process on it. And this process, say Unix process, has identifier 1, 2, 3, 4. And so the ILA address, this logical virtual address, is a Facebook 1, 2, 3, 4, well, double colon. The machine has a locator, a /64 prefix FC00 cafe, right? So this gives it like a full-blown ILA machine. Logical address, locator. On the other hand, you have similar symmetrical machine. This one also has a process identifier and physical locator. So how these two talk to each other? When you send packet from host 1, what happens? This is a packet as the application sends it, right? Both addresses, source and dest, are logical, ILA addresses, right? They have Facebook prefix, all great. Application isn't aware of anything else. Once this packet crosses the kernel layer, we rewrite the destination address with a locator. So now the packet can be routed because locators are visible in the underlying network. So this is kind of this underlay separation, but there's no tunnels. We simply just rewrite. So now it's like on the wire, after NAT, you can route this. And because the locator points to the other machine, you get to the other guy, and we do another translation. And now we see the original packet, which has the original logical addresses. And so both processes, they're not even aware of all this NAT magic. They think they have this logical addressing like all along. So you can think of ILA as giving this like, perception of a large virtual cloud that shares the same /64 prefix. Like every process in this cloud has /64 prefix, Facebook, and they all have this logical addressing, right? So they talk to each other. They're not aware of this underlying network. They simply send packets. So basically, the analogy is very similar to like having like a virtual /64 subnet, except there is no ICMP here. All right. SIR prefix. So I mentioned this multiple times, right? SIR prefix is this /64 bits in the address that remain constant. This is how we hide these locators from the applications. I think Tom changed this a few times, the definition of this prefix, of this term, but so far it's standard, it's fine representation. Probably the most important part about this thing is that the ILA routers have to inject this into the IP network. And the reason for that is to attract traffic from non-ILA hosts. Because ILA hosts, they already know, OK, I have my cache, I can translate, I can send packets directly to the other guy. The non-ILA hosts have no idea about the structure. So we attract their packets by doing this, the injection of this prefix. So the next diagram kind of illustrates this. It shows you how the ILA router works. So on the left side, you have 3 hosts, ILA hosts. They have these caches, they have the kernel function, and the ILA router in between acts as an intermediary. It injects this SIR prefix in the network. Say in our case, using BGP, you like peer to a rec switch, you inject it, it flies out. The non-ILA host is now aware that it can send packets to this ILA prefix, the SIR prefix. When they send packets to this logical address, Facebook something, colon, something, we hit the router because injection, right? And you can scale this by using any cast, like multiple routers injecting the same prefix. Once we hit the router, what happens is a translation, right? The router has a full map. It does this magical rewrite and sends packet to the ultimate destination, to the ILA host. The best part is on the return path, you don't have to go across the router again because the source addresses are modified. So you can simply send packets directly back. This is like logically very, very similar to the, how we call this DSR, direct server return, in the load balancing world. So ILA routers is a very important concept because this is what makes, as I mentioned before, ILA practical. You can deploy this ILA hosts incrementally. They talk to each other, all great, but everyone else can use these ILA routers to talk to these hosts. So obviously you have these problems, kind of scaling capacity and so on and so forth, but you can easily estimate that. Well, depends if you have tooling. And then put these more boxes if you need more traffic to accommodate. OK, just to recap on the ILA router, because it's so important, it's a proxy. It has a full mapping cache, just like ILA host, and it kind of bridges packets between two domains. So I think like so far we have all the buzzwords. We have ILA address, ILA router, and server prefix, right? And they all kind of form this full picture of like ILA domain talking to inside each other, inside this domain, and between domains. OK, so now next logical question is control plane. I mean, all these caches won't build themselves on their own, right? It's great. I mean, you can do this manually by hand, punch all these entries. So control plane was never defined, right? Pretty much like you need something to publish these mappings between machines. And in general, there's two systems that can do this, two system types that can do this. The push one and the pull one. So everyone knows the BGPs. Still, I think, BGP is kind of push system. You can publish something, it propagates everywhere. I mean, if you have out-reflectors, there's some limitations. But the idea is, in a push system, you broadcast information. I mean, you can use multicast, like an VXLANs if you want. It's nice because it's simple. I mean, BGP isn't that simple, but the idea is simple. The pull systems like DNS, right? When you request something and you get a response. So pull systems are difficult, more difficult to operate, but they're more scalable. The difficulty comes mostly because you decouple the query and response. You have to cache it locally, invalidate, and so on and so forth. But in general, the push systems are much simpler to operate and debug. You don't have to kind of spend time looking at the difference between local cache and remote system. So usually, like, logically, when we decide to build control plane, we built something broadcasty. So we didn't build new protocol. As I said earlier on, we just used a special backend system to publish these mappings. OK. Yeah, just like explains. Like, as I said, we have a push-based system to propagate mappings at Facebook. Every host writes its local mappings, its cache, to some backend, say, OK, this is my mappings, my processes. And then somehow this propagates to all our machines. How exactly? We'll discuss a bit later. But what's important is that all the hosts and routers receive the same mappings. So kind of broadcast, it doesn't sound super scalable, but it works pretty well so far. OK. The most fun part is how can you implement identifiability? How can you move this ID between machines? So I have a probably nice diagram for this. In this diagram, we have 3 ILA hosts. So all these machines, they have ILA stack. So we have these mapping caches and so on and so forth. We have 2 processes on host A and B, and they talk to each other, right? C talks to B, and so on. And now the job scheduler decides to move one process to a different machine. It doesn't happen very often, but it does happen. What happens next is your flow becomes invalid, because this mapping is no longer valid. You remove it from cache, and what's going to happen next, you simply black hole packets. So like originally in the ILA, we thought, OK, we can send redirects and so on and so forth, tell, OK, this is invalid. For now, we decided to keep it simple. So at this point, we simply drop packets. As a next step, host A broadcasts to everybody using publishing system, saying, OK, I now have this ID at my machine. And every host can now update the mapping cache. And now the flow recovers. Because you have a new entry, OK, packets can go further. So it kind of sucks. I mean, you can say because, well, hey, we drop packets, right? It's not like instantaneous moves. There is no state preservation. On the plus side, it's super simple. So in most cases, the time it takes to move the task and set it up on a different machine is longer than it takes to update the caches. So in most cases, I'm pretty much everywhere, we never see any problem with this. So when you shut down a task and you move it, by the time you start the task again, the process on a new machine, you already have the mapping engines everywhere. And on plus side, this broadcast mechanics is super simple to debug. And like simplicity is probably the most important thing when you do something like a larger scale. You really don't want to spend time debugging like 10,000 machines or maybe even more. OK, so now the real deal, the deployment. So we discussed a few aspects before, but let's going to go over some more details. So before we discuss deployment, I want to say a huge thank you to the team that made it all possible. So I give a talk here, but this was a work of multiple people, and I think some of them are here today. Huge thank you to all of you. It wasn't possible without your help, people. All right. OK, so first step. When we had this idea of ILA last year, I think this was kind of March or April last year, the first question is like, OK, we need to deploy these /64 prefixes on every host. And we have lots of machines to configure. But the first thing and foremost, you have to enable the new address plan in the network. Because by last year, we already have V6 everywhere. We have this like addressing plan deployed. And now we have number one. So we began by saying, OK, let's kind of over-provision things. And on every rec switch, we configure a bunch of static routes, /64s. Nothing fancy, no injections, just static routes. So these were pre-programmed for all possible machines you can have under this rec switch. The next thing, I mean, on the rec switch, of course, you summarize them. Because you don't want to inject all this stuff into the network. And after this, you kind of go up and up, you do summarization. And our data centers, they have this kind of three-layer hierarchy. There's rec switch, there's a pod or a fabric switches, and there's a spine. So all of them kind of summarize gradually. And it shows the boundaries such that you can fit in lots of addresses. So I think Mikhail had to request a bunch of /42 prefixes from IANA and LACNIC just in case. So we have like lots of address space to use now. And this allowed us to be pretty, I would say, flexible in terms of allocation. Oops, that's the last one. So pretty much the idea was, OK, we have /42. We can allocate up to 32 data center addresses blocks from this single prefix. All right, host configuration. So we just discussed networking stuff. So networking stuff wasn't that easy, but it was rather simple. We had to modify the tools to do provisioning, but initially just like broadcast changes everywhere. You push all these configs everywhere. That part was easy. I can tell like trying to maintain it wasn't so easy, but it's a different story. OK, so you have to configure every machine with a /64 prefix. That part was rather easy conceptually. You simply modify a chef recipe. The support was like that big of a change. The biggest challenge, probably this took like 1 month to deploy, maybe even more, simply because when you push new address to every machine, you often break some random stuff. Like this was really surprising. As you push a simple change, you realize people have some weird assumptions. Like people often have a code that does address enumeration on a machine on their own way. Or they assume they're going to use this address always. The biggest problem was automatic binding. When you do a connect out of machine, the kernel picks up your address, right? And when you add new address, this causes like lots of things to break. So I think we pushed this initially. We broke some stuff, pulled back, pushed the game, break some more things. I think we even tried to kind of decide where should we put this new address. This was a big discussion. Should we put this on the ETH0 or a different interface? Oh, this will break something else, and so on and so forth. It was a really fun story, by the way. But eventually we pushed everywhere. But the good lesson is basically a very simple change. When you push it to lots of machines, will break something, and people will be mad at you eventually. So this is an output from my machine. It shows the 6 addressing, right? So you can see the ETH0. With lots of fancy numbers, you can see there's 3 addresses there. Of course, this link local. You can get it this guy. There's the old one, 2401, is the one we had before on every machine. And there's this golden one, 2803, and it's /64, not 128. And that's the one that ILA requires on every machine. And it says deprecated. So who knows what deprecated means in IPv6? But exactly, right? Not really. So this is a funny story. Apparently, V6 doesn't have exact rules for picking up an address when you do a connection. There's like a RFC on this saying, OK, this is like 10,000 like different exceptions. But the thing for us was, OK, we put this new address on ETH0. We don't want people to use it by default. So it comes out in the 6, you can change the lifetime of address to 0. So once you make it lifetime of 0, you can still use this address, but the kernel will not automatically bind to this address. And somehow IP route shows this as deprecated. I mean, this is confusing, but this simply means that you won't use this address by default. So you have to bind to this address explicitly. And people often ask, oh, why did you deploy this on ETH0? Because definitely this was a pain to roll. But as we deploy this on different interfaces, we broke something else. And eventually, after some back and forth, we kept all addresses on one interface on every machine. And yes, like in most cases, I would say pretty much everywhere, we have one interface in every machine, ETH0 only. OK, so now we have this locator. So the great part now, you have this locator, it gives you address pool per host. And so you can take a /64 pool and allocate addresses from it. So the job scheduler can say, OK, as I start a process, a task on this machine, I can give it an address from this pool. Pretty easy, right? So this is the initial implementation. Actually, this is how it works right now, is you start a new job, you allocate address from local pool using a simple random number. You just say, OK, pick up random 64-bit number, prepend this to a prefix, and give it to a task. So remember, this right now, there's no ILA. So you simply use the /64 on the machine as a pool to draw addresses. So even if you say never deploy ILA, mobility, all these kind of things, you can already use this functionality to give unique addressing per task or per process. And obviously, as you have seen before on previous slide, the ::1 is given to the machine itself. So you can number the existing processes. So next question was, hey, OK, nobody cares about addressing. Like when people run the tasks, they just say, oh, bind to all addresses, bind to in other any, or in 6 other any, whatever. So how can you force application to use the address? It comes down to be very trivial. Like the probably best way is to pass address in environment variable and tell the process, OK, if you're aware of this, use this address. Unfortunately, people don't like changing code. So they usually, oh, I want to change my stuff. So make it magical, make it happen. So the next thing was hacky, using LD_preload. So who knows what LD preload is? Anyone? OK, so you know it's hacky, right? It's horrible, but it works. So this was the first implementation. Say, OK, LD preload intercepts system calls, right? Like system calls to sockets, and replaces the address with this ILA address, this local address. So this works surprisingly well. It does have some performance overhead, but you only see this on a very, very intense connection rate. So surprisingly, all these hacky and dirty things really kind of work really well. And right now, this is the way we do is we tell the application, hey, use this address, or we'll force it to use it. So people always ask, hey, why not containers? Like, why not namespaces? Because you have containers, right? You can have all this cool stuff. Docker has namespaces. So alas, namespaces are great. Unfortunately, they create some caveats. The biggest one is, if you worry about this, is loopback interface. Every namespace has its own loopback interface. And comes out, many tasks get used to using loopback interface for communications to each other. Like we have some shared service in every machine, and people talk to it, right? Or this loopback. It's really convenient for people and applications, but makes it kind of hard to move on namespaces. So at this point of time, we do have experiments with namespaces, but we kind of still prefer, at this point, to use one namespace, default namespace for all processes, simply because it doesn't break many things. You'll be surprised like how many of these kind of small assumptions cause you so much pain as you move forward. But it's probably one of the biggest lessons you learn is some innocent assumption like, oh, well, this should just work. Will probably echo back to you like in 5 or 4 years. OK, so it's great to have these addresses, right? Unfortunately, people don't like memorizing IPv6 addresses. It's apparently very difficult. There's too many bytes there. It was great to have a DNS name per container. Kind of obvious, people like it. But it was also debates, pretty much, because we have internal systems that don't use DNS, and it was a fun discussion. But in the end, we now have some system that allows you to create a name per container. DNS name. So we publish and propagate the records PTR and quad A as you start up a container. Luckily, the addresses don't change often, so it doesn't create too much stress on the system. And propagation time is probably on 1 minute. So the biggest use case for DNS names is mostly debugging. When people look at the logs, they like seeing some logical names, not some address. Because especially if you look at this address, OK, what's next? You can trace, so you can ping it, or you have to SSH to it. And as you have these additional steps or indirection, people really get kind of not like that, because debugging gets more complicated. So DNS names are mostly for convenience. We don't use them, say, to do host selection or load balancing. It's mostly do you have something in your logs to look at. OK, so now is next question. OK, this is great. ILA is kind of amazing. Does kernel support this? So first of all, this is Linux kernel only. It says kernel, but it's Linux. As you can imagine, if you folks use FreeBSD, there's no ILA there. Maybe not yet, I don't know. Actually, does anyone use FreeBSD here? OK, Linux is the king so far. Maybe Windows, I don't know. So kernel has this thing called LWT, lightweight tunnels. This thing allows you to kind of slap encapsulation packets as you route them. I think who worked on this? I mean, people use it a lot these days. I think this is how we do BXLine or other stuff. Right now, we use LWT in kernel to do all the ILA magic. So Tom Herbert wrote this stuff for kernel. Now in the routing table, you can do address rewrites and back and forth translate them. All programmability is via Netlink API. And I mean, who doesn't like Netlink? It's amazing. It's so painful to debug if you have tried it. But so there's one kind of caveat right now. It's all there in kernel. The documentation is kind of lacking a little bit. So if you want to program ILA, for example, you have to look at source code of IP route tool, for example. It's not too difficult. It just takes a few additional steps to see how things work. This is an example. I mean, you can configure ILA on a host without any netlink. You can shell IP route command. It just looks ugly. But here's an example. So when you start with ILA, the first thing was mod probe ILA. Because ILA right now is a kernel module. It's sort of in kernel right now. So this command is probably painfully familiar to everybody. This creates a local ILA address and binds it to loopback. So simply say you have cert prefix, and your identifier is 2555 something. And then this creates a mapping entry. So for the identifier, Facebook, blah, 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 something, you say use this locator. So when a packet hits this rule in kernel table, you do rewrite. You rewrite the identifier, so you write the SIR header with 64 bits of a locator. Notice you have to use via. So via in this case is gateway, default gateway. And the last rule is kind of the reverse. This one creates local mapping. It says, OK, if packet comes in for my cert prefix identifier, do the rewrite reverse and send it to me. So basically it says, if I see the locator, do the rewrite and send this to the loopback. So word of caution, I think this changed in kernel 4.6 onwards. The syntax is similar but slightly different. This is, I think, was based on 4.0 kernel initially. We had the first version of ILA. So what about ILA routers? So the previous stuff was for ILA hosts. 3 commands with ILA hosts. So it comes out ILA router is not different. It's pretty much the same. It just has more routing rules. So you enable routing table. You add all these mapping entries. And this packet hits the router. You do routing lookup and translation. So this one caveat, right? It isn't super fast, right? So using the kernel router isn't super great for performance, but it kind of works right now. We have other things which I can't talk right now because there's not enough time to accelerate these things in kernel using BPF and other cool stuff, but there's simply not enough time to cover this today. But our initial implementation was simply using the kernel routing table. So all you have to do is create a bunch of routing rules, and they just work. And also, initially, in our deployment, our implementation, for simplicity, we made every ILA host be an ILA router. A little bit comes a bit crazy, but it works pretty straightforward. You inject this cert prefix from every host. It looks like you inject this prefix from 1,000 machines, right? It sounds crazy, but works pretty well. And it just makes things simple. You don't have separate roles. You have like one package on every machine. All right, control plane. I think you're almost there. It's getting close. So control plane is how we did this mapping dissemination. So you have to synchronize the caches between machines. On this diagram, we have 3 ILA hosts. And these guys need to synchronize the mapping tables somehow. So you got container stuff on one machine. All this guy does is write in database. So ZPDB, I think, is I'm not sure the open source, but we have some public talks about this. It's a key value store. These are cool these days. Everyone has key value store. It's distributed. It has its own synchronization, propagation. So it kind of was a little easy way out. We didn't have to build like our own complex system. For disseminations, you simply write the database, and everyone else simply downloads this data periodically, say every 5 seconds. So ZPDB is kind of not very fast on writes, but very fast on reads. And writes are infrequent. So in our case, it was probably, I think we said it's 5 seconds. So after 5 seconds, you will propagate all mappings everywhere. And in our case, ZPDB has this async replication between regions. So you propagate these mappings everywhere across like the whole network. And you don't have to kind of build your own networking stack or like control plane. I mean, this is kind of a little bit of cheating. We didn't have to build fancy stuff, but it was really easy to implement. And it works. And most important thing, it actually works. OK. Just to give you some impression, so ZPDB, we use it like, to publish and pull data from the database, right? Nothing fancy. In fact, this is like a simple process which periodically scans the table, pushes it, pulls it back. Like very simple, very reliable. The scale of deployment isn't that big right now. It's mostly been now done for testing and experimentation. Like tens of thousands of hosts is like one cluster or something. We don't do much mobile tasks. We have virtual addressing, but it's infrequent. It doesn't change often. So the write rate is very, very low. And so right now, we use very actively unique address per task. We don't use mobility very actively right now. It's mostly being kind of tested on per task basis. Like somebody wants a mobile address, OK, there you go. You take it, you use it if you want. OK, operational applications. I mean, a change that big, like ILA, definitely has some implications, right? You can't just get away with like, doing like nothing. So first and foremost, ILA breaks ICMP, right? Because you do this rewrite, all the devices in transit have no idea about your changes, right? As they respond back, they have the address which is unknown to the host. The same for trace route, right? So we quickly found out these things were broken. And right now, there is no fix in the kernel. So next thing was, OK, well, we got to fix this. We have a fix for this right now. I don't think it's upstreamed yet. It's using BPF programs to fix this. But this was probably the major thing we encountered when deployed this. And this is very, very important, because people really hate when they can't trace route or they see something broken. I mean, people get really upset if they see stars on a trace route, you know. So this was the first thing to fix. I would say, aside from the breaking some applications as we pushed the ILA addresses on every host, this is the next big thing to fix. And then pretty much everything just works, right? So it works, it's great. OK. If I have to summarize this talk, this was a long talk. Thanks for holding with me, guys. ILA is address per process, first thing. It's address mobility, location dependence, and best, it's IPv6 only. You can do this in IPv4. There's still not enough bits. And with this, I would like to thank you for listening, and we'll take your questions.
One question, Petr. So yes, so how it works pretty well for the end-to-end host, the ILA. How would you go with adding the service chaining to this kind of conversations to cross, let's say, firewall between any two processes?
So we don't do this that much at Facebook. You know, service chain wasn't like a priority. In theory, we discussed this. You can do multiple rewrites if you want to on multiple hosts, like ILA routers, if you want to chain it. It's like in PLS. You can kind of swap the addresses on the path. It was a great discussion, but nobody needed this. Like for most times, we use proxies if we need some intermediate function. So we explicitly require applications to be aware of a function in between. It's not like in the web environment, you don't see people often kind of slightly transparently. People like to be explicitly aware of a change in the network.
Related question.
Yeah.
So in data center environments where you want to have micro-segmentation and security, so you may want to have layer 3 stateless firewalls on the network side where you want to drop certain packets based on the source or destination IPs. If you're going to do the translation, which is probably happening at the host level itself, so the underlying firewalls will not work.
So I think, so first of all, as I explained, there is no segmentation naturally, right? But you can definitely have firewall rules based on logical addressing. Like in our case, all the filtering, if we have to do it, is done using BPF programs, which we didn't discuss today. But if you're curious, I think there's an open source project called, I think, Cilium, and they kind of go all the way depth, showing how you can do filtering using BPF programs. It's totally possible. You just have to synthesize policies and push them to every host to deploy this isolation. But it's basically kind of Echoes on steroids. Not IP tables, we don't use IP tables, but BPF programs can do this for you. So you can attach a program that does filtering for you. And the nice part about this, you can filter on logical addressing. So you don't have to filter on these physical underlying addresses. You can give like a whole domain one prefix, logical ILA prefix, and filtering becomes much, much easier, in fact. But we just don't do this right now because we don't have the need to segment the applications.
Hi. So going back to your addressing scheme, 64 to hosts, /32 allocated to the data center. Am I correct in presuming that you're using ARIN or other registrar space and not ULA private space for that?
Oh yes, definitely. I think Paul insisted we're going to be public addressing. I was like, hey, you can just cheat and do something simple. Yeah. But we had to request like.
Okay. But add a statement. There seems to be I've encountered a misconception among a lot of people that when you go to ARIN or the other registries for space, that documenting your existing usage only applies to space that you're routing over the internet. Internal usage such as this absolutely counts when you're applying for public space.
So if you're curious, again, I think Mikhail is here. He did always like talks to Iana and Lachnik to justify this. And I think it wasn't that difficult. Maybe just yell at them, I don't know. He has all the experience talking to them. Like, I think it took like a week or two. Like, it was a very quick process for Mikhail to finish this conversation. It wasn't, okay, well, it was for me.
I think the thing that people fail to realize is that in ULA, you can only use a 48 at a time. And that's the big issue. And when the registries actually countered back to Mikkel on this, we just countered back saying, read the RFC, and then they just gave us the space. Who's next?
Thank you, Peter. This is so good. I'm so astonished. And thank you so much for sharing this, Peter, as well as the team. And I have two questions. Oh, by the way, I'm Kay from DigitalOcean. First question, I think that's simple. So you said IPv6 only. And if I want to use this ILA and make this container speak to IPv4, what is an option? That's the first question. Oh, maybe.
Okay, I can answer this. So we discussed this option of having v4 machines. It's possible in the ILA, because you have 64-bit, to embed v4 address. So if you have the NAT on machine, you can have v4 address. It's like similar to, how do we call this? God. Is this technique that they announced?
CDN?
Like, yes. Basically, you can do translation pretty much. With so many technologies in v6 translation, I got lost there. But pretty much, you can embed v4 address in v6 and do this rewrites. So this allows you to have v4 machines talking to v4 or v6. As for v4 talking to v6, I mean, that's a classical thing, right? You have to use like DNS64, other things. You have to do NAT as well. Definitely, internally, we weren't focused on this because we're v6 only. Like, all our front end for v4 has proxies. So we have v4 blocks, and the proxies we do with translation. We don't do NAT, but we just do proxying for this function. If you would ask me, I know I don't like NAT that much, especially stateful. People have been, I think, very successful using stateless NAT to do with rewrites, but we prefer proxies because it's much more flexible at the application layer.
Sorry, thank you. And the second question is actually, this is the first time to go through this ILA, so maybe I'm making a stupid question, but about the naming part for 64-bit lower part, and you said that is mapped and that is kept from host
application.
Container A to container B.
Uh-huh.
Which means that a 64-bit part should be identical across the entire network?
Yes. So in our case, it's like kind of this one prefix, Facebook, right, logically. It could be multiple, but then you have to kind of explicitly use ILA routers to talk between domains. So you can have multiple ILA domains, and they talk to each other using ILA gateways, ILA routers as well. It's easier to have one prefix everywhere. It just kind of limits your scalability because you have to share the same mapping system. But it's totally possible to have multiple sort of prefixes. It's just that between these domains that have different prefixes, you have to talk via the routers, via ILA routers, because you're not aware of the mappings in the other domain.
Right. Thank you.
Sure.
All right. Thank you, Peter. We got to get on to the next talk.
All right. Thanks, guys.